Well, let's get nice and icy today. We're going to talk about glaciers. Well, glaciers is an immense field or stream of ice that's formed in a mountain region where the snow doesn't melt. It just keeps accumulating. And then this material, as it builds up, slowly moves down a mountain slope or a valley, like it does in the Alps or in the Andes, or over a much larger area, for example, Greenland, or even the biggest one, of course, Antarctica. Glaciers are especially common in polar regions, but they're also found at all latitudes, including near the equator. Used to be that people didn't think that it was possible to have to have a glacier near the equator because it's so hot. But if you get high enough, you can have glaciers, and we'll see some. There's about 80,000 of these in the world. So here are the components of a glacier very simply. Up where it's cold is the accumulation zone. The snow just builds up there. And as the snow piles on, it compresses the snow at the bottom, and that becomes ice, and that becomes part of the glacier that's moving down the hill. And then way down at the bottom is a place where the ice melts. This is the ablation zone, and we'll see several examples of that. And in between is sort of the place where uphill the ice is accumulating, and downhill it's moving. So, glaciers can move forward if there's more accumulation than melting, or they can retreat if there's more melting than accumulation. All right, so glaciers currently cover about 10% of the Earth's surface. Most of it's tied up in Greenland up here, or in Antarctica down here. And then the rest of them are scattered through regions like the Himalayas and the high mountains of Central Asia, few down here in that part of Asia, and over here in the Alps. Of course, up here by Alaska and British Columbia and Yukon. And then the places we're going to talk about here in Latin America. Now, glaciers lie above the snow line, and the snow line in the Americas changes a lot. So here we're going from the North Pole to the South Pole, and what we're seeing is two things. One is the elevation, right, this jagged line with the diagonal, and the other is the snow line. And what you can see is near the poles, the snow line is basically at sea level. But as you approach go farther and farther south, it becomes higher and higher till in the Americas, in Latin America, it's mostly above 5,000 meters. And we can see immediately what we're going to talk about in the rest of this lecture, which is there are a lot of glaciers in the Andes. There are a few glaciers in Mexico, and there are no glaciers in Central America. Just not high enough. All right, let's start off with Mexico. And here we've got Mexico City, the capital. And here we have the three glaciers of Mexico. They're all on these tall volcanoes, Popocatépetl, Iztaccíhuatl, and Quitlaltépetl, or Pico de Orizaba. These are the three mountain volcanoes that have glaciers on them. It's very small, only about 10 square kilometers. And they're all very small except for the one on this volcano, which is 9 kilometers. And all of them are receding. So here's Popocatépetl. This is an Aztec name which means smoking mountain, which is well named. It's the second highest peak in Mexico, and about 20 million people live within about 80 kilometers of Popo. And it's erupted at least 36 times since the Spanish conquest in 1522. So here is the glaciers of Popocatépetl. This is the summit region of the volcano and its crater. And they're all on the north side because the north side gets less direct sunlight than the south side at this latitude. And so, here's a scale. So you can see they're all less than about a kilometer. So here we've got a view of Popocatépetl and Iztaccíhuatl. And you can see that Popocatépetl got snow on it, and so does Iztaccíhuatl. So this is the Aztec for Sleeping Woman. It's the third highest peak in Mexico. You can see it from Mexico City. It's an extinct volcano, so no danger of it erupting. And these are the glaciers that are on Iztaccíhuatl. So that's a kilometer. So you can see these are all pretty small volcanoes. They're near the summit region. This is a big ridge that comes down here. And they're on either side of this ridge. Now, this is El Pico de Orizaba, or Citlapetl, which is the highest point in Mexico, third highest peak in North America, and it's an active volcano, last erupting in 1687. And the glaciers, again, are on the north side of the volcano. Here's the summit region, and again, because the sun shines, it's warmer on the south side. The north side is where the glaciers are. Now, Pico de Orizaba is a hazardous volcano, and we talked about what can happen when you have a volcanic eruption and you have ice on the top of the volcano when we talked about Nevado del Ruiz and the lahars that happen from a relatively moderate eruption. So there's considerable concern about what's going to happen. And so there have been several eruptions in the last few thousand years. The last big one was about 3,400 years ago. And these arrows show the paths of the older Nue Ardents that came out of there. So there's some concern about an eruption that would have a catastrophic effect on the glaciers of this volcano. Now, heading south, we go to Central America. And it's easy to discuss the glaciers of Latin America because there are none. This is the highest peak in Central America, Volcan Tajamuca. It is the highest point, only 4,200 meters tall. It gets some snowfall, but it doesn't last. It's not tall enough. All right, now we get to the Andes, and in the Andes is where we find our Latin American glaciers. So they have glaciers from Venezuela all the way down to Tierra del Fuego. And there's glaciers that exist depending on latitude, altitude, and annual precipitation. And we'll talk about the largest of these, which are in the Patagonian Andes in the far south, at the end of this lecture. And it's the largest, the southern Patagonian ice field is the largest glacial field outside of Antarctica in the southern hemisphere. And the northern Patagonian glacier ice field is the second largest in Latin America. All right, so here's where they are, and here's what we're going to talk about. So up here in the north, in Venezuela, there's about 2 square kilometers of glacier. In Colombia, there's much more. In Ecuador, there's about the same amount. In Peru, there's much more glaciers. In Bolivia, there's a fair amount. And Chile and Argentina have the lion's share of the glaciers of Latin America. And we'll be talking about these in order. All right, so let's talk very briefly about Venezuela glaciers. So in the Cordillera de Merida, in sort of northwestern Venezuela, you have these high mountains, and you've got 5 glaciers with a total area of about 2 square kilometers, not very big, on 3 separate peaks here in the Cordillera. And these are shrinking very, very rapidly, and they'll soon be gone. So Colombia now has got many small glaciers, and the largest glaciers on Nevado del Ruiz. We've talked about this volcano before, and then several other areas in there, which is Nevado del Tojimo, Nevado del Huy, and Nevado del Santa Isabel. All of them have glaciers on them, but the biggest one is on Nevado del Ruiz, and we saw the consequences of an eruption on that volcano. Ecuador has more than 100 small glaciers with a total area of about less than 100 square kilometers. And they're on 4 high summits of the Cordillera Occidental and 13 mountains of the Cordillera Oriental. So the Occidental is in the west, and the Oriental is in the east, and here are all the glaciers, small glaciers of Ecuador. This is an example of Cotopaxi, which is a beautiful stratovolcano, big volcano in Ecuador. It's had more than 50 eruptions since 1738. It's almost 6,000 meters tall and stands more than 3 kilometers above the surroundings. And this base of this volcano is 23 kilometers across. It's a big volcano. Now here you can see the ice cap of Cotopaxi. And it, interestingly enough, lies almost exactly on the equator, but it has a very nice accumulation of ice and glaciers that go down the slopes away. And you can see how the glaciers extend farther in this direction than they do over in this direction. And that's because of where the dominant moisture-bearing winds are. The winds are coming this way, so there's more snow on this side of the mountain than on this side of the mountain. Then you can also notice these deep meltwater channels, which are carved by meltwater off the volcano and also lahars. And one of the lahars from 1877 traveled almost 100 kilometers from the volcano. Now we get to Peru. And Peru is, a large country, and it has many volcanoes. And here we can see the headwaters of the Amazon coming out, and then the mountains off to the west. So there are many glaciers in Peru, but we're going to talk about a few of them. Here you can see in green all of the glaciers that exist. Here's Cusco, the ancient Inca capital. Here's Lima, the modern capital of Peru. And we're going to talk about Calcaya. So here we can see these glaciers in a little bit more detail. This is Nevado Huascaran, which is a very famous glacier and volcano. This Cordillera Blanca is well named because it's covered in snow, is the most extensive tropical ice-covered mountain range in the world. And this is where most of the glaciers are in Peru. So, like many other glaciers around the world, the Calcaya Glacier is retreating. Now, this is only good sort of through the late 1990s, but you can see in these colors it's showing you where the edge of the glacier is. Here in 1963, it was all the way out to here. 1978, 1983, 1991, 1995. And as the glacier pulled back, a lake formed in the region where it was before. So here we've got a picture of it in 1983. The ice is coming down to here or so, and now it's back here, 1991. So when we wrote this lecture, the main ice tongue is retreating at almost 150 meters per year, and that melting is producing this lake there. So what we're going to do now is watch a video, about 5.5 minutes. I hope you enjoy it. It'll talk about some of the challenges that the melting glaciers are creating for the people that live near the volcanoes, near the glaciers.
Nuestra comunidad de Pucaromi está ubicada en las faldas de Alzangate. Está rodeado con las montañas más hermosas, que está cubierto de bastante nieve. Del nieve nos nace el agua y por el agua nos vivimos todos. El nevado de Azangate para nosotros o para la comunidad de Pucarán es tan importante porque de él vivimos. Del Azangate tomamos agua, también el agua utilizamos para regar los pastos, para hacer la agricultura. Para eso el Azangate es mucho más importante para nosotros aquí en la comunidad de Pucarán. Estamos sintiendo el cambio climático, ¿no? Que está afectando fuertemente, ¿no? Para nosotros con ese desgaste de nieve que está saliendo poca cantidad de agua, entonces es un factor climático que nos está causando, ¿no? Un gran daño para nosotros. Yo cuando era niño, yo veía el Azangate más blanco, pero ahora de año a año está bajando, ¿no? De poco a poco está volviéndose negro el nevado. Con esa falta de agua, nosotros no podemos regar la cantidad de terrenos que tenemos para que crezca los pastos. Entonces, a falta de pastos, los animales como alpaca, como la oveja, ellos no pueden crecer fácilmente. Al comer poca pasto, no crece la lana de alpaca. Ahora, preferimos comprar lana sintética del mercado y tejer chompas, chalenas, chullos de la lana sintéticas. Y también en esas partes donde sembrábamos, no se puede sembrar ya papas nativas. En las partes bajas donde necesitan regar el terreno, no hay suficiente agua. Por eso estamos sembrando las papas nativas en partes altas. Pero según que está pasando año tras año, las partes altas también ya se está acabándose ya. Entonces, años que vienen después, no vamos a tener en dónde sembrar la papa nativa. Y es prácticamente lo que vamos a perder la papa nativa, ¿no? Lamentablemente el terreno no resiste ya el sembrío de papa nativa. Y por eso ahora estamos cambiando de cultivar papas mejoradas, que es con abono químico. Necesita dinero para comprar esos abonos, pero más antes no era así, solamente con nuestro abono de corral nomás. Todos los comuneros también están preocupados y no tienen qué hacer, no tienen qué decir sobre esta causa. Mi preocupación es al ver a mis hijos que cuando se acaba una vez el Azangate, cuando se acabe el nieve, no sé qué vamos a hacer. Solo Dios lo sabrá de nosotros después, cuando se acaba el agua y el nieve.
Hope you enjoyed that. Now let's move on to Bolivia. So Bolivia is very close to this high region of Peru, and so there are many glaciers in here. And there's almost 560 square kilometers of glacier in Bolivia. And mostly it's on the high peaks of the Cordillera Oriental in here. And there's not enough rain down here to, or snow on these peaks to provide enough for glaciers in these regions. All right, so here is the Bolivian glaciers coming through here. And pay attention to these lakes. These finger lakes are good indications of where the glaciers used to come. So those glaciers carved out embayments and also dammed the downstream part with the debris that they left behind. And as they retreated, they left these lakes. And you can look at them and immediately see where the glaciers used to be. All right. Now, these glaciers in Peru and Bolivia are at very low latitudes, and these low latitude glaciers provide the best record of climate in Latin America, because you can core the ice and then figure out when that ice formed and measure some things in it and get a very good idea of how the climate has changed. And the challenge is that because these glaciers are shrinking rapidly, this record will soon be gone. So for example, Cocaya has shrunk by at least 20% in the last 60 years. And so people want to core this ice and study it while they can. So I'm going to talk a little bit about oxygen isotopes, because one of the main ways that we determine paleoclimate is by looking at the isotopic composition of oxygen. Now, where's the oxygen coming from? Ice is H2O, so oxygen is a critical part of water and ice, and so the oxygen isotopic composition in that water or ice is recording something about what was happening when that snowfall happened. So let's just talk a little bit about isotopes. So, and we'll focus in on oxygen isotopes. So there's three stable varieties of oxygen. One of them is oxygen 16, so that's 8 protons and 8 neutrons. One's oxygen 17, 8 protons and 9 neutrons. Oxygen 18, which is 8 protons and 10 neutrons. They're just varying by the number of neutrons. So they have a different mass, but they behave exactly the same in the way they bond with hydrogen or anything else. Now, in fact, 99.6% of all oxygen is oxygen 16, and only about 1 in 2,000 oxygen atoms contains an extra neutron in his oxygen 17. But it's a little bit heavier than oxygen 16. And 1 in 500 contains 2 extra neutrons and is about 10% heavier. And that's oxygen 18. All right, so we can measure oxygen isotopes in the mass spectrometer. Now, you have to take the material that you want to analyze and pass it through a bunch of chemical separation, and then you introduce it into a machine and you accelerate it through a magnetic field, and that separates the different masses into different rays that are easily counted. You don't need to worry about the details. It's not going to be on the exam. But the thing that is worth knowing is that water with oxygen 16 is going to be lighter than water with oxygen 18, because 18 is 10% heavier than 16. And so if you've got water with oxygen 16, it's going to evaporate more readily. So in general, because rain forms from evaporated seawater, the rain is going to have relatively less oxygen 18 than the water from which it evaporated from. So these variations in 1618 are very small, but this equipment is remarkably sensitive and able to detect this. Now we talk about this in a way that you don't need to know for the test, but this funny value, this Greek symbol delta, that's the little Greek symbol delta, sometimes called del, is del notation. And so we can talk about these very small variations, say in oxygen 18, using this kind of a formula. So the ratio of 18 to 16 over the sample minus that of a standard, which say is seawater, modern seawater, divided by that of the standard by 1,000 is that value of del 18. So you don't have to memorize this, but it makes it easier to see small variations if you multiply it by 1,000. So by definition, seawater has a del 18 of 0. So if water has more oxygen 18 than seawater, it would be heavier, and if it's got less than seawater, it would be lighter. Oops. Yeah, that's right. All right, so now let's go to Peru Great Glaciers. We're going to take two examples. One of them is Huascaran, and the other is Calcaya. And these two volcanoes, Huascaran is the highest one, and it's the coldest, and they were drilled, and basically it's not difficult drilling. You just have to core it with pretty much just gravity. And Calcaya is a little bit farther south and is a little bit lower down, but both of them were cored. So just see where they are. Here's Calcaya down here, and here's Huascaran up here. Now, Calcaya has got this beautiful stratification, it's layering. So here you're seeing the end of the glacier, and you can see this huge cliff, 55 meters tall. And what you see are accumulations of ice and then dust layers. Accumulations of ice and then dust layers. So most of the snow falls between November and April. That's what the ice layer is. And in the rest of the year, wind-blown dust accumulates, and that's the dust layer. So basically, these are, you're counting years here, right? We're not going to count them here, but you can count backwards in time and get a very good age when this layer was deposited. And so you can accurately date when the ice core, particular parts of the ice core accumulated. So let's climb up the glacier and take our gear and do some ice coring. Now another one is Sajama in Bolivia. So Sajama is very close to Peru. Nice volcano, nice summit glacier here. It's the highest peak in Bolivia, and there's a glacier that's about 115 meters deep on top of the summit. So here's how we do ice coring. You just need a metal tube, and you need something sharp to cut through the ice, and you need something to keep the ice from falling out when you pull it out. So let's watch a 3-minute video about ice coring and what happens when the local community is suspicious of the activity of scientists. So this is an interesting story because the community could see the scientists going up to the mountain, and they wondered, what are they doing? Are they going to be taking our silver again? So let's watch the movie. Hope you enjoy it.
Lonnie Thompson, distinguished professor at The Ohio State University, and an international team of scientists were sampling glacial ice at the summit of Huascaran, located in a rural part of Peru. Their work is likely to shed new light on Earth's warming climate, and while they had obtained permission and permits from the federal Peruvian government, the local villagers had a history of distrust with the federal government.
They were very upset at the fact that we were drilling ice cores. They thought we were looking for gold, that we were working for a mining company. They were upset because the president of Peru had come to visit us in a helicopter and had not bothered to stop in their village. They were upset for a number of reasons, but their argument against us was that what we were doing was polluting their glacier and their water supply.
At the start, the villagers said they wanted the scientists off the mountain within 12 hours. But the team had many tons of equipment and some 470 meters of ice core samples. The scientists told the villagers they could not possibly leave that quickly. The villagers gave them 2 days.
Fortunately, when they insisted we stopped, we had just completed our second ice core to bedrock on the summit, and we were finished anyway.
Hasta luego.
So we then had everyone off the mountain, so people were safe. But still we had our ice and our equipment was up there.
The team met with the mayor of the village and told him that they needed 5 days to get their equipment and the cores off the mountain, that leaving the equipment behind would be polluting, and that they were hoping to study the ice, not destroy it. The mayor agreed, but he said it was up to the villagers. So Thompson and the team, after a long conversation, agreed to meet with the villagers and hear their complaints.
We are sorry that we did not stop the motion at the beginning to explain to you exactly what we were doing.
The villagers ultimately agreed to give the scientists 5 days to remove their equipment and the cores from the mountain.
Glaciers, it doesn't matter whether you're in Bolivia or you're in New Guinea or you're in Tibet. Glaciers are sacred places. They're places where the gods live. If you're working in a remote area and an area where indigenous people have lived for thousands of years, you're the outsider. And first of all, you don't judge what they believe or they don't believe. And I tell my students, my graduate students, it's very important to be very competent in what you do. But I said, it's even more important that you learn people skills and how to get along with people. And the best way I know to get along with people that do not understand you is you go and you stand in front of them and you tell them, where you're coming from and how. And what you're hoping for is to make a connection.
For Ohio State News, I'm Laura Ahrenshield.
All right, I hope you enjoyed that video. So let's look a little bit more about how precipitation and oxygen isotopes work. So basically, the Delo 18, you remember what that is, goes from light to heavy depending on temperature. So this is all relative to standard mean ocean water. But the warmer the environment, the higher the Delo 18, and the cooler the environment, the lower it is. And that's because it's easier to evaporate the heavier oxygen water in warm water than it is in cold water. So here's an example. Here we've got a map of oxygen isotopes in the United States water. So what you can see here on this scale is going from heavy, this is heavy up here, to light, right? Delo 18 of minus 18 is lighter than a Delo 18 of minus 2. So down here in the south, in Florida and Texas and Louisiana, we've got relatively heavy oxygen in our rain. And so you can see that. And in contrast, up in the Northwest, in Montana and Oregon and Washington, they have much lower Delo 18. So you can, by measuring the oxygen isotopes, if you want, you can get a sense of the temperature, the annual temperature of a region. So we can use this to interrogate ice cores and figure out when the climate changed. So here, for example, is interglacial, which is a time when the Earth was relatively warm, versus glacial episodes. So when you have a glacial episode, you've got a lot of ice. And when you have an interglacial, you have much less ice. And what that means is that because this water ultimately comes from the ocean, if we put a lot of light oxygen on the ocean, on the continent in ice, the ocean will become heavier. And correspondingly, when we melt a lot of that during interglacial times, the ocean will get lighter, right? So here we see during interglacials, it's relatively light. The ocean is relatively light. During the glacials, it's relatively heavy. So here we've got del 18 value going back through time, and here with 0, and then all of a sudden, sometime in the past, it dropped. It increased, I'm sorry, to about 2. So this is clearly, an interglacial time, and this is a glacial time. We can just look at it that simply. So here are the results of ice cores from Sajama in Bolivia, Huascaran in Peru, and we can compare that with Greenland, Western China, and a couple from Antarctica. But what we see here is a real change in del 18 from about minus 21, right, over here, to about minus 16 or 17. So there was a big step, an increase at about 11 or 12,000 years ago. We can see that spectacularly on Sajama. We can see it to a certain extent on Huascaran. We see it in Greenland pretty well. In China, not so much. In Antarctica, not so much either. This is the kind of results that people who work on the isotope stratigraphy of ice cores use to interpret the climate record. All right, so from this we have, and other studies, we have a sense of how South America changed between modern times, when we have these kinds of zones. We can see the glacial regions, and then the tropical and subtropical rainforests, the savannas and cerrados, and things like that, to the last glacial maximum, when there was much more glaciation in the high mountains. The tropical rainforest was much smaller because it was drier. The savanna and cerrados was a much larger part of Brazil than it is today. The entire continent was very different only about 15,000 years ago. Today, only about 5% of South America could be classified as desert. But during the last glacial, it was at least 25% was desert. All right, so that was Calcaya and Sajama, and we're going to jump down now into Patagonia. And in Patagonia, the relief gets much lower, but the snow line gets even lower, so that in parts of Patagonia, you've got large areas that are above the snow line. And unsurprisingly, you have a lot of glaciers down there. So, Chile and Argentina have these glaciers. And so we've come down from Peru and Bolivia, and in the high mountains of Chile and Argentina, there's some scattered ones. And they become more and more as you go south. But by the time you get down into Patagonia, southern Patagonia, there's some big ice fields down there. All right, so now we can look from space to see what's going on. So here's the Atlantic Ocean over here, And here's the Pacific over here, kind of hidden. And you can see this is a very green part of Chile. This is the temperate rainforest that we talked about. And then here you see two big ice fields. One of them is the northern Patagonian ice field. The other one is the southern Patagonian ice field. And you can see these lakes marking where the old glaciers used to go. Beautiful. You can see these glaciers going down towards the sea over here. Now let's zoom in a little bit more into the northern Patagonian ice field and the southern Patagonian ice field. And it's very extensive. You know, this is 46 degrees south. This is 52, it's 6 degrees of latitude, or almost 700 kilometers. All right, and as we said, those lakes in southern Chile and Argentina tell you where the old glaciers went, because they carved them out and then they deposited all kinds of material at the ends. So it makes these big lakes. You know, the glaciers, there's no glaciers here now, but there were during the last glacial episode. All right, so now we're focused clearly on southern Patagonia. Here we can see the border between Argentina and Chile and Tierra del Fuego. And here's the northern Patagonian ice field, and here's the southern Patagonian ice field. And this is the ice field of the Cordillera Darwin. We won't talk much about that. That's almost to Antarctica. Now, you can also see in here these end moraines, which tell you, it's basically piles of sediment that were dumped when the glaciers ended. And so there are, there's one at 18 or 19,000 years ago, this red line, and then a younger one at 10 to 13,000 in this blue line. It sort of tells you the waxing and the waning of the ice of this big ice field. Let's watch a 1.5 minute video. This is actually an advertisement for tourism, but I think you'll find it just as much fun as if you were planning a trek down to this region. Hope you enjoyed that. So now let's take a little bit more look at the northern Patagonian ice field. And it's basically a remnant of a much larger field that existed. And you can see that it's pretty big. It's about the size of Dallas, maybe twice the size of Dallas County. And like many glacial areas in the world, it's in retreat. but it's getting plenty of moisture and stays cold enough to stay for quite some time. And it's got 28 exit glaciers. You can see them here. Here's an exit glacier going down a valley, another one, another, here's another. And these carved valleys that end up being lakes after the ice retreats. This is kind of a sort of a perspective view of the North Patagonian ice sheet, and here you can see some of the exit glaciers coming down these valleys, both regions. That's okay. That's okay. So this is an example. This is the San Quintin Glacier. It's the largest outflow glacier in the northern Patagonian, and so we're looking at it two times, in 1994 and in 2002. And you can see that it is retreating. Here you can see it's sort of in this lake that it made from its, rimmed by its own debris. And the ice is sort of pulling back from this little lake over here, almost gone there. Now let's go to the southern Patagonian ice field. It's much bigger. It's about 13,000 square kilometers, almost 360 kilometers long, and on the order of 40 kilometers across. And there's nearly 50 significant outlet glaciers, and these can reach the sea and make fjords. And then the ones that go into Argentina, they make these finger lakes, and you can see them here. Let's watch a 2.5-minute video. This will be another sort of a tourist video, but I think you'll find it very enticing. All right, so this is another view of it looking straight down from satellite images. And here's going off to the west, east, So this is going to be south and this is going to be north. And here you can see the fjords that lead to the ocean, to the Pacific Ocean. And here you can see these Finger Lakes where when the ice was much larger, it carved this out. And today they're nice big lakes. This is another view. Now we're looking south. This is the southern Patagonian ice field, and here are these big Finger Lakes coming out into Argentina. You see how dry this part of Argentina is. It shows up very, very brown. Here's a view of the southern Patagonian ice field. You'll feel like you're in Antarctica in this region. It's quite spectacular. Now, Bruggen Glacier is the largest one of the outlet glaciers in the southern Patagonian ice field. So here you can see the ice sheet, and here you can see the ocean. This is Illrampu Fjord, and basically it's coming out here, it's coming here, coming here. This is actually sort of a lake that's sort of blocked off from the sea by this glacier. And you can see how the position of the glacier has changed. Interestingly enough, it is advancing. So it's thought that the glacier is about here in 1830, and then here in 1945, and then in 1976, it was here and here. So as we noticed, other glaciers, nearly all other glaciers around the world are in retreat, but Glacier Bruggen is advancing. So let's watch a 30-second video about this. Hope you enjoyed that. Here's another glacier coming out of the southern Patagonian ice field. This is Glacier Viedma, and here we're sort of looking from the Argentina towards the southern Patagonian ice field, and this is Lago Viedma in Argentina. Now, as we said, the Patagonian glaciers are melting rapidly in general. This is a scientific study showing the thickness change in meters per year versus elevation. And so basically you can see that the glaciers are decreasing in thinning most in the higher elevations, whereas in lower elevations, they're not changing as much because basically all of the ice is gone. Now, with the shrinking of the Patagonian glaciers, it's going to have an effect on sea level. Sea level rise is a concern because many cities are right at the coast, but the Patagonian glaciers contain a relatively small proportion of all of the ice that's on the continental ice sheet. So during the 30 years up to 2000, these glaciers lost ice at a rate equivalent to a sea level rise of only less than 1/10 of a millimeter per year. And that has doubled to about 0.1 millimeters per year. Sea level is presently rising at about 2 millimeters per year, but the Patagonian glacier shrinking are only contributing about 5% of that. All right, I hope you enjoyed that lecture. We've talked about some beautiful places in Latin America, but in many ways, some of the most beautiful are the Patagonian region especially the Chilean rainforest, which leads directly up to these glaciers. It's quite spectacular if you ever get a chance. So, our next lecture will be on the Amazon River. See you then.